So welcome to lecture number 12, supplementary session 2. In this session, we will talk about a special topic in linear momentum, and that is collision or impact. This is something that you already have done or studied in your JEE examination, but it's worth discussing this and a couple of problems on this to apply this important topic through the idea of linear momentum and impulse. So impact or collision is a process where the internal forces act for a very short time and during the impact or the collision, and these forces are typically large as compared to other kind of body forces that are acting on the masses in general. And the impact or collision is a complex process. It involves internal material deformation and recovery, and that we'll discuss, and it also results in a generation of sound and heat because of loss of energy in many situations. So we'll talk about two different kinds of impact. So one's called direct central impact, and the other one is oblique central impact. So central is because the forces are from center to center. So during when the impact happens, so we'll have typically a scenario where we have a mass m1 that is moving with a velocity v1 towards m2, which is moving with a velocity v2. Okay, and v1 has to be greater than v2 if the impact will happen. So we're talking about the first scenario here, that is direct central impact. Okay, so this is before impact. Now then the impact will happen, and when the impact happens, for a brief amount of time the bodies will be in contact with each other. So we'll have a deformation phase where the bodies will be getting closer to each other, and there will be a moment when the two bodies, that's m1 and m2, have reached the situation of maximum deformation. So this is maximum deformation. So at the situation where you have the maximum deformation, that is the bodies will not come closer to each other, relatively. So if you are sitting at m1 and you see m2, it will not come any closer. So it will not, the surfaces will not deform any further. So at that situation, both the bodies will be moving at the same speed, let's say v0. And then once they have reached that situation where they're moving together and the maximum deformation has been reached, then starts the process of restoration. So in the restoration phase, now the bodies will move away from each other relatively, in the sense that if there was a spring between them, the spring during maximum deformation has reached the maximum compression, and now the spring will start to expand. So this is restoration is going to happen, and then after impact, when the impact is over, the first will move with the velocity v1 prime, and the second moves with the velocity. We're talking about direct center to center. So this, in this case, it's only the magnitude that matters. They're moving along a line from center to center here, and then after impact, and this is what we have, and in this case v2 is going to be greater than v1 because now I'm sorry, v2 prime, that's right, so v1 prime will be less than v2 prime, because now the collision has happened and the bodies are now going relatively, they are moving away from each other. Okay, so if I was to look at one particular object, so what I would see is during the deformation phase, there will be a force, well during the complete collision process, in fact, there will be a force acting. So let's say if I was only considering m1, so in m1 there is a force acting because of the other object, and it's always from right to left, so that is acting in the left direction. So this is for the case where the bodies are getting closer to each other, it's called, we'll call this the deformation force. And once they have reached the maximum deformation, and now the bodies will start to expand again or restore again, so this process, the force is still in the same direction, but we'll call it the restoration force. So in this complete process, from the beginning of the impact to the end of the impact, we'll see that the object m1 will get decelerated and object m2 will get accelerated, because on m2 the force will be acting in the direction of its speed, at least the way I have shown. If m2 was moving towards m1 for some reason, that's how the situation was given. In that case, there will be a deceleration of m2. Now the linear momentum of the system will always be conserved, because the forces between the two bodies are equal and opposite. So if Fd acts on m1, then similarly on m2 Fd or Fr will act. Okay, so they will be equal and opposite. So momentum is conserved, linear momentum is conserved. Of the system is conserved. System constitutes the two particles. So linear momentum of system is conserved because the net external force acting on the system is 0 during the collision. We are neglecting the body forces, which for example mg, that may be acting, and they are very small as compared to the very large forces that act on the bodies during collision. So we can write the initial momentum of the system, that's m1 v1 plus m2 v2, that will be equal to the final momentum of the system. So this is regarding the conservation of momentum. Now what about energy? The energy may not necessarily be conserved, the mechanical energy, that's what we're talking about. And the reason is because that depends on the nature of the internal forces that act on the bodies during collision. So if the internal forces were conservative in nature, so in that case we call the collision process elastic. think of it as a spring. So if there was a spring, that was when we talk about deformation of bodies, let's say actually there was a body and then there was a spring connected and there was another body with a spring connected. So it's actually what happened was during the collision, or we can just assume one spring and a body. So when this body collides with this body, it basically just compresses a spring, nothing else happens. Let's say these were hard spheres and they were connected to a spring that could compress. So in that case, the internal force is purely due to the restoration force of the spring, and that is conservative in nature. This is just a way to understand, of course, just to model the problem, but realistically we may have, it depends on the material of the bodies under contact. So if the materials are, let's say they were rubber and the collision was not very severe, so the deformation of the balls was not very severe, a slight deformation. So for small deformations of rubber, we can say that the spheres, rubber spheres, can be considered to be completely elastic bodies. So typically this happens when less severe impact so the impact is more severe, then we'll expect some sort of loss of energy. So the forces then become non-conservative in nature. And we also say that restoration, because remember the collision is a two-stage process. There's one that is deformation when the bodies get closer to each other, and then the next is restoration. So restoration is regained, we can say that. Complete restoration is regained, or restoration is regained. So next one is when you have non-conservative internal forces. So in that case we call it inelastic collision. So in this case we may get permanent deformation. And energy is lost. As heat or sound, and also as sometimes elastic waves. Okay, that get dissipated in the object. So this typically will happen when the impact is more severe. And the restoration in this case is not regained completely. Now when I say restoration is not regained completely, so how do we quantify that amount of restoration? So for that we have a quantity that we have defined called the coefficient of restitution. With the symbol E. So it's defined as the capacity of the contacting bodies to recover from impact. Okay. So we define it as the ratio of the magnitude of restoration impulse to the magnitude of deformation impulse. Okay, so if I was to use symbols, then deformation happens between time 0, that is when the impact starts, to some time t naught, which is the time when the two bodies have reached the maximum deformation, that is when they are moving together with the velocity, let's say v naught. So from 0 to t naught of the deformation force, because deformation force acts during this interval, times dt. So that's the magnitude of the deformation impulse, and on the numerator we have from t naught to, let's say, time t when the contact is released, and that is or when the collision ceases, and that's the restoration force times dt. That's the impulse of the restoration force that acts when the objects start going away from each other, right? And we can think of worst case scenario where the two bodies stick to each other. You may have done these kind of problems where there is, I mean, the bodies can compress, but as they're completely plastic in nature, so they will not have any tendency to rebound. It's like clay. So the two clay balls, they collide. So when the two clay balls collide, they will then, they will come closer to each other, and when you push the balls together, there will be some deformation force, but there is no restoration force. Once they have reached that situation where they are both moving together with v naught, there is no restoration possible because clay is almost completely plastic. So then what you see is that they will keep moving together with the velocity v naught because there was no restoration. So in that case, Fr is 0. There is no restoration force at all, so the numerator becomes 0, so E is 0. And we know that these kind of collisions are called completely or fully inelastic collisions, where there is no restoration force at all, and in that case the coefficient of restitution is 0. So it varies between 0 and 1. Right, so this I mean, how do we find these? Because we know about the integral form of the force momentum relationship, or we know that initial momentum plus the impulse is equal to the final momentum. Okay, so we use this impulse momentum relationship on we can apply them on the two different objects because the two different objects colliding. So let's say this is m1 which first collides. So during the restoration phase, the deformation phase, the mass has a force Fd acting, and then there is the restoration phase where again it's in the same direction but it's a different force depending on the nature of the materials. So if I was to write Fd, integral Fd dt, so that is nothing but the change in the momentum of my first mass from 0 to t naught. So if we call that, if we know the velocity, let's say call v naught as the velocity, that is the velocity with which both the particles move together when they have the maximum deformation. So we can write this integral, that is denominator, in terms of the initial velocity of the mass m1, that is v1, and v naught. So this simply becomes m1 v1 minus m1 v naught. So that's the loss in the momentum of the first body, and that is nothing but that's due to the impulse of the deformation force. Similarly, in the numerator, there is a further loss in the momentum of the first body between maximum deformation and release, and that is because of the restoration impulse. So this simply becomes v naught minus v1 prime upon v1 minus v naught. Right? And similarly, we can also write this for the second object, because the second object is also going through the same deformation and restoration forces. So this the restoration force becomes m2 v2 prime minus m2 v naught divided by m2 v naught minus m2 v2. So we'll call this 1 and we'll call this 2. And if I solve 1 and 2, and remember they both denote the quantity E, I would want to get rid of V naught here, because V naught is something that is not, it's an intermediate situation that is not of interest during this discussion right now. So what we'll do is we'll use 1 and 2 to eliminate V naught. And that gives us the expression for E. That is something we have known from our previous understanding of collision. So that is equal to V2 prime minus V1 prime upon V1 minus V2, which is nothing but the velocity of separation to the velocity of approach. You can do the algebra yourself. So we see that E is equal to 1 when the impulse, the restoration impulse, is the same as deformation impulse, that is no energy is lost. So E equal to 1 is fully elastic impact, or we'll just say elastic impact. So there is no energy lost. The capacity to recover is the same as the capacity to deform. Then E equal to 0 is fully inelastic impact. There is some energy lost. Well, fully inelastic does not mean all energy is lost. All energy lost means the particles will stop moving, but that is not the case. Okay. So capacity to recover is less. Well, in that case, capacity to recover is 0. That is the case of fully inelastic. So this is plastic collision. It's called the plastic collision, and this is a typical example is two balls of clay. So one ball of clay is moving and the other ball of clay is moving, and they both collide and they start moving together with the same speed V naught, because there is no way they can recover. Now this E, the coefficient of restitution, is basically dependent on many things. The most obvious to think of is the material, and as I told you, it also depends on the severity of impact. So the impact is very severe, the forces involved are very large, then we will see that E is different from gentle impacts. So this is dependent on the impact relative velocity. Okay. So if you take two objects which are moving at a very large speed relative to each other, then you can expect E to be less than 1. It also depends on geometry, whether two spheres or two solids they hit each other, two spheres or two cuboids. So it depends on the geometry and shape, and even roughness, finish, and so on. So here's in fact a graph of E versus the impact relative velocity. That is nothing but the velocity of approach. So we see that when the velocity of approach is very low, it will be close to 1. and as we start increasing the impact velocity, it becomes smaller. So for a given material, let's say steel on steel balls colliding, so we'll see that it will have this kind of a nature with the impact relative velocity. And if I take glass colliding with glass, then we'll have some situation where E will be higher than what we get for steel on steel. And a perfectly elastic body, which is just a theoretical concept, always has E equal to 1, and a perfectly plastic body will have E equal to 0, and real bodies will have E which is somewhere in the intermediate range. So this is glass on glass, and then we can have okay, and so on. So let's do a quick problem on direct central impact. So we have so let's say we have two balls. The first one is M, the second one is 3M. They are moving on a line directly from center to center. I'm sorry, central impact actually refers to a situation where the bodies are moving from center to center, and in this case we have the first mass moving with the velocity v, and the second mass moving with the velocity v but in the opposite, the speed v in the opposite direction. So that's the situation before the impact. So we have to find out what are the velocities of the two masses. So since I do not know the direction, I'll take the right direction as the positive direction. So they move with v1 prime and v2 prime, and we have to find, so this is after collision, so we have to find v1 prime and v2 prime. It's a very straightforward application of the ideas of collision that we have developed through the conservation of angular momentum and energy dependent on the coefficient of restitution. So conservation of momentum, mv plus 3m times minus v, that's equal to m v1 prime plus m3m v2 prime. So we have two unknowns, v1 prime and v2 prime. So that's the first equation, and the second equation now comes from, well, it is given to us that E is equal to 1 here. So that comes from the ideas of coefficient of restitution. So we'll call it energy. So energy is conserved, so half m v squared. You can also use E equal to the velocity of separation divided by velocity of approach. It's up to you. So we have two equations and two unknowns, and that's v1 prime and v2 prime, so we can solve it. And this actually gives us a quadratic in the unknown, and well, it could be v1 prime or v2 prime, whichever you eliminate from the first equation. And this quadratic will give us two solutions. The first one actually is the same as what the initial condition is, because that's also a solution to the quadratic that also satisfies these momentum energy conservation. But that is not of interest because that is what we already know, that is before impact. So the after impact solution you will get is v1 prime equals minus 2v and v2 prime equals 0. So that is the solution. So that says that the first object, which is lighter one, will rebound with double the speed, and the second one will come to a stop. Right. So the next topic is the topic on oblique central impact. So in this case, what we have is the velocities v1 and v2 for the objects. They are not parallel but in the same plane. And then they collide. So we have a direction in which the bodies collide, and we call this the normal direction, and there is a direction that is perpendicular to that, that is the tangential direction. So after collision, the bodies will rebound the first one we'll say goes with these are vectors v1 prime, and the second one goes with v2 prime, and the angles they make are theta 1 prime and theta 2 prime, and initially before the impact they were making angles theta 1 and theta 2. So this is the convention that we are using. So we have the unknowns v1 prime and v2 prime in the normal and tangential directions. So the unknowns here are the vectors, or we can say they are components in the two directions. So let's write the unknowns. So the unknowns are v1 prime in the normal direction, that's a component of v1 prime in normal, then v1 prime in tangential, then we have v2 prime in normal and v2 prime in tangential. So we need four equations, four scalar equations. The first one is going to be the momentum conservation for the system in the normal direction, because the collision is happening in the normal direction. So the system as such, its momentum will be conserved. In the n direction, so that becomes m1 v1n plus m2 v2n so this is the conservation of momentum in the normal direction. And then we have two equations that are coming from the momentum conservation of the two particles individually in the tangential direction, because there is no force in the tangential direction. So the impulse of the force in tangential direction is 0. So that means the momentum for the first object in the tangential direction is its momentum in the tangential direction after impact. And then we have another equation that's coming from the energy ideas. And that is quantified through the coefficient of restitution. So that's the velocity of separation divided by the velocity of approach. And this is all in the normal direction because the collision is happening in the normal direction. There is no collision in the tangential direction. So we have 4 equations and 4 unknowns. So this can easily be solved. But the only problem is it becomes quite hectic algebraically, and managing this becomes a bit too tedious. So for that we have an interesting alternative to this approach, and that is called the analysis of collision in C frame. So the C frame is the center of mass frame. So till now whatever we were doing is from the L frame. Okay, so this L is called the lab frame. So our origin was somewhere other than the center of mass. So this is as if you are measuring things in a lab. Both bodies were moving with respect to the origin, that's a lab origin. So now what we'll do is we'll analyze this collision in the C frame, and the reason we can do that is because the center of mass is not accelerating during collision. The collision forces are internal, so they do not result in the acceleration of center of mass. So the center of mass velocity during the process of collision is the same. So if I was to take a C frame, that is the origin fixed at the center of mass of the two objects, then I would end up having a Newtonian frame of reference, that is an inertial frame of reference. So my laws of physics are valid in that frame as well. So let's analyze collision in the center of mass frame. So velocity of the second object before collision is v2, the vector, and then we have, let's say, v1 as a vector that denotes the velocity of the first object before collision. And then since we need the center of mass velocity here, which is vcm, and that's defined as m1 v1 plus m2 v2 divided by m1 plus m2. So if I want to draw the vector, so since we have v1 and v2 as shown in the figure on the left, so vcm is simply going to be a vector with its arrow on the line that is joining the two vectors v1 and v2. And that's easy to see. And then since we are analyzing the collision from the center of mass frame, that is C frame, we'll have to write relative velocities. So v1 with respect to the center of mass, so that is the vector v1 in the lab frame minus vcm in the lab frame. So if we substitute vcm as what's shown in the expression above, we will get v1c, which is simply m2 upon m1 plus m2 times the vector v1 minus v2, and v1 minus v2 is the vector, let's use blue color, it's basically this vector. So we will call this V relative, V rel. So we can see that V1C is along the direction of V relative, that is that joins V1 and V2, and its magnitude is such, I mean the way it's defined is V1 minus VCM. So we can see V1 and VCM, so let's use red color to denote that. So V1 minus VCM is basically this vector, that is along V rel, which has a magnitude that's given, that's in the ratio of m2 upon m1 plus m2. So this we denote as V1 with respect to center of mass. And similarly, if I was to draw V2 with respect to center of mass, so that becomes this vector, that's V2 with respect to the center of mass. So it's in the opposite direction as V1C with a different magnitude, of course. So since we have V1 and V2 with respect to center of mass, or in the C frame, so we can write the momenta, that's P1 in the C frame, it's m1 V1 C, which simply becomes this quantity m1 m2 upon m1 plus m2 times V rel. Similarly, the quantity P2 in the C frame is minus m1 m2 upon m1 plus m2 times V rel. And this quantity m1 m2 upon m1 plus m2 sorry is denoted by mu, which is called the reduced mass. So this basically becomes mu times, let's write it here, so this is so P2C is minus the reduced mass of the system times V relative. So this is a very interesting thing that we notice from here, that the sum of the momenta, that is P1C plus P2C, is equal to 0 in the C frame, and in the L frame P1 plus P2 is simply m1 V1 plus m2 V2. I mean, since it is the same, we can either use the initial, that is before collision velocities, or after collision velocities, and this is nothing but m1 plus m2 times VCM. So this is in the L frame, and since we know that if you are going from L to the C frame, we are sitting on the center of mass, so this automatically becomes 0 because VCM minus VCM is 0. Okay. So this could have been concluded the other way, just by using L frame and then going to the C frame, still we would have got that the sum of the momenta in the C frame is 0. Right. I mean, we can use any approach, both approaches are fine. It's just that the C frame approach is analytically more simple or simpler as compared to the expressions we get in the L frame. Now in C frame, I mean, although we would not go into that much of a detailed discussion, so typically what we see is that the particles are deflected. So when I say particles are deflected, I mean when I'm talking about the velocities with respect to the center of mass C. So what we'll see is in C frame, if you have, let's say this is V1 C, so what we see is there's a deflection, so this vector will rotate somehow, so this will be V1 prime C, there will be a deflection angle alpha. And if I look at V2 C, and I already know the direction of V2C is V2 minus VCM, so that is going to be in the opposite direction of V1C. This also gets deflected by an angle alpha. So we see a deflection in both these quantities. Now of course finding alpha is not straightforward, although we can find the deflection angles in the L frame, but finding alpha that is in the C frame is only possible if we know what is the nature of the internal force acting on the particles, as opposed to when we calculate deflection angles theta 1 and theta 2 in the L frames, which are not dependent on the nature of internal forces, but the alpha is. So don't try to find alpha, because finding alpha depends on your knowledge of the internal forces. But this is how typically you will see the vectors behaving in the C frame. Now let's look at one particular problem, which is a slightly simpler case of elastic collision. So we'll take a problem. So it's a completely elastic collision, that is the coefficient of restitution is 1, and we'll analyze it from, it's an oblique elastic collision from C frame. So is there something interesting that happens if we put this restriction of the collision being fully elastic? So fully elastic means the energy, kinetic energy, is conserved. So in the C frame as well, I can write half m1 v1c squared plus the kinetic energy in the C frame of the second particle. By the way, if you're trying to find the energy from an L frame, we know that kinetic energy is this quantity plus the kinetic energy of the center of mass, that is half times the total mass times the VCM squared. But that is something we won't get here, but the conservation law can still be applied. And we also know that the sum of the momenta is 0. We just showed that in the C frame. So we get m1 v1c plus is equal to 0. So we have three equations here. and we have the unknowns v1 prime c with respect to c and v2 prime with respect to c. So I would want to find what these quantities are. So when we use these equations, of course I cannot use these two equations to find v1 prime and v2 prime. So I basically use this and this to solve for v1 prime and v2 prime. This simply gives us some sort of compatibility between v1c and v2c. So once we solve this, so what we get is v1c is equal to v1 prime c. Now this is oblique. So oblique, the magnitude of the velocities before and after the collision in the C frame are the same. So what that means is that in the C frame, for this case of a fully elastic collision, what happens is the velocity vectors of the two of the mass, let's say mass number 1 here, it simply rotates, it does not change in magnitude. It's a very interesting thing. And similarly, if we do for the second mass, we will get a similar relation. So we summarize. They only rotate, and we already showed that the angle of rotation or deflection is alpha in the C frame. So their length will not change. But does that hold true for inelastic collision as well? So does the above hold true for inelastic collision too? If you think about it, let's take a very simple situation where two masses are moving along a line, and one of them is stationary. So let's say this one moving with the velocity v. V is fine. It hits a mass where the velocity was 0, and they start to move together with v naught. That's a fully inelastic collision. So if they start to move with v naught together, what we see is that the center of mass also moves with v naught. So the velocity of the two masses with respect to center of mass is 0. Okay. So the magnitude does change, because in the beginning the velocity of the two particles with respect to the center of mass was definitely non-zero. So I mean, whenever we want to disprove something, the easiest thing is to think of a counter example, and this is one. So we cannot say that this statement is true for inelastic collision as well. This is only for elastic collision, but that does help us a lot in using this idea for elastic collisions. Now let's try to solve a problem of oblique collision again. So we have a mass. There are situations where one mass is moving and the other mass, it's not a center to center now, is it won't hit along a point which joins, which is in the direction of velocity. So the collision will happen somewhere in this position along this. So this will be our tangent line and this is going to be our normal line. So this is stationary. So if we find, if I try to draw the triangles of velocity, so we find v1c, well we can simply draw it. So we have our vector v1 and this, let us say, is vcm, because m2 is stationary. So our vcm is simply along v1, just reduced in the ratio of the how the mass m1 is with respect to m1 to m2, the sum. And then by the definition of v1cm, this is what v1cm is, v1c. Sorry. Now after collision, we expect this m1 to get deflected in this direction. So we expect some sort of a v1 prime that is in the lap frame like this, and from the definition of v1 prime c, it will look something like this, and the deflection angle here is theta 1, and the deflection angle in the C frame is alpha. Now this is for the second mass now. So for the second mass, v2c looks like this, because this is nothing but negative of the velocity of center of mass. Then we have v2 is 0. Now we expect this mass to get deflected and go like this. So that is going to be the direction of v2 prime. So we expect the v2 prime to be something like this, and from that reasoning, since this is our vcm, so we get our v2 prime with respect to c as this vector. So again we see a deflection of alpha, and theta is this angle. So this is the velocity triangle for the second mass, that is m2. Now depending on the problem, you will have to draw this and then geometrically infer many ideas, but I simply wanted to draw that to demonstrate how it looks. Then depending on the problem, you can use the ideas. So let's solve another example, another problem. So in this case we have three cars, all identical. So there is a car A that is moving with a velocity of v naught, with a speed of v naught in a direction towards car B and car C. All three cars are identical, although they don't look like that. Now cars B and C are parked, and the brakes are not engaged. So we expect that the A car colliding with B and C will result in them to move as well. So car A plows into B and C, which are parked without brakes. And the collisions are completely inelastic. So we have to find out what fraction of total energy is dissipated in car C due to collision. Right. So let's try to find that. So the first collision we get is between A and B. So in that case, when we apply the momentum conservation, so we have before the collision we have m v naught plus 0, and after collision both A and B will move with the same velocity, let's say v1. So we have 2m times v1. So we'll show A and B that move together with v1. Okay, so this is linear momentum conservation, and then it's completely inelastic. So we have used the idea of them moving together. That basically tells us that the collision is inelastic, that is E is equal to 0. Right, so this gives us v1 is equal to v naught by 2. So the two masses, the two cars A and B will start moving together with half the speed of what A was. And then collision 2, the bunch AB that's moving with v naught by 2, it collides with C, and that results in A, B and C all moving together with v2. So now we apply the conservation of linear momentum. So 2m moving with v naught by 2 is equal to, and there's no momentum for C in the beginning, and then we have all three masses 3m moving with v2. So that gives us v2 is v naught upon 3. So that's the speed with which the three cars will start moving together. So we can find for this collision number 2, the initial kinetic energy was half times 2m times v naught by 2 squared, which is m v naught squared by 4, and the final kinetic energy is half times 3m times v naught by 3 squared. That is half m v naught squared by 6. So the change in kinetic energy, because remember we're trying to find out how much energy is lost, so that is going to be the change. Should be the other way around. So Ki minus Kf is m v naught squared. So we get 3 minus 2, so that's by 12. So that is the energy lost in collision 2, that was with car C, and the total energy that the car A had before it started colliding, K naught, was half m v naught square. That was the energy that we had started with, kinetic energy. So this we can see that delta K in car C upon K naught is 1 upon 6. So the question asked was, what fraction of energy is dissipated in collision with car C? That is 1/6. 1/6 of the energy, initial energy, is dissipated in the collision with car 6. Now, of course, the system still has some energy. Some of it got dissipated in the collision between cars A and B, and some of it is dissipated in the second collision, and the system has its energies. If you add them, you should definitely get the initial energy that you started with. So that solves the problem.